We're on air, so let's get started. My name is Sébastien Bratières. I wear two hats professionally. One is I'm doing PhD research in Zubin Garamani's group at the University of Cambridge in the Department of Engineering. I do research not connected to deep learning and not connected to speech recognition either. I work on probabilistic machine learning, mainly Bayesian methods. And my second hat is in industry. I work for a small German company called Dawin. We make speech recognition interfaces for industry users. So people who use speech recognition systems in the industry, like in plants or out on the field or in manufacturing, for instance, or in logistics. So we make very custom applications for them. The background, my educational background is in speech recognition and natural language processing. And it's always been a subject I've been very fond of. So this is what I'm going to speak about today. Let me try share the slides now so I can get started on them. There we go. So get my slides here. The thing I'm going to speak about, or the message I'm going to argue mainly, is that there's been a change in the last 3 to 5 years in the technology used in speech recognition. So what I'm going to argue specifically is that the state of the art has changed from using, I'm going to define all the terms later on, but this is just an outline, right? Between using what's, let me try and point here, what's here, so Gaussian mixture models and hidden Markov models, and using n-grams as the part of the engine that is called the language model. Again, I'm going to define what this is, to using, in both cases, neural network-based machine learning models. So in this case here, these guys have been replaced by deep neural nets, so feed-forward neural nets, and n-grams have been replaced by recurrent neural networks. So that's all happened in the last, 3 to 5 years. If you go historically, and if you don't do research, you can argue that this happened in the last 10 years, probably. So I'm going to speak about this, and I'm also going to give you hints of what's going on more on the research side of things. There are very exciting things happening there. And specifically, well, still in the both areas of acoustic and language modeling. The acoustic models are now tending to be replaced by convolutional neural nets, and language models by LSTMs. And then there's a radically new thing, which is completely taking apart the classical model of speech recognition. So no longer using this divide between acoustics and language, and that's called the end-to-end approaches. Let me just change the way I present the slides on my PC here, and I'll go to the next one. So ASR systems are deep down the probabilistic models. So they are parametric probabilistic models. So that's important to understand because it means that they are big mathematical models that will take as input, obviously, some audio, and then they output something probabilistic. Namely, they output a measure of a match between the audio that the engine has seen as the input and a hypothetical or a candidate word sequence. Okay, but it is hypothesizing that the output could be. So you're getting probabilities as the output, a measure of a match. And because it's a parametric probabilistic model, you have those three usual steps in training and testing your model. Namely, you have the training step where you're learning parameters. So your model contains or is defined by a set of parameters, numbers, real numbers, scalars. And these numbers you will define based on training data. Then you have a cross-validation step that's also pretty usual in all sorts of supervised machine learning methods, where you're learning what's called hyperparameters. So in deep neural nets, typically these things are the number of hidden layers or maybe the size of your model, or maybe the type of neuron, sigmoid or rectified linear unit or such that you're using. So these are all things. These are all things that are important to understand. And then obviously the last one is the recognition step, where you are trying to recognize some incoming audio and you're outputting what I just described before. I've got the admins telling me that there's some noise on the line, so let's see if I can do anything about this before I go any further. Maybe I'm not using the microphone that I'm expecting to use. Sorry guys, but that's probably for the best. Yeah, indeed, I'm not using my headset microphone. Is that any better? Is the audio better now? Is the audio any better now? It should, yeah, right. Okay, got rid of the noise. So let's get back to the slides here. Cool. Admins say it's not better. Well, if there's so many of you saying that it's better, I'll believe you and not the admins. Okay, so right, back to training and then doing some recognition with the speech engines here. So yeah, so I've detailed these steps because it's just to illustrate that a recognition engine, a speech recognition engine, is just another type of supervised machine learning model, and it gets trained exactly in the same fashion. There's no sort of artificial intelligence, sorcery, or wizardry or magic in here. It's just plain machine learning. Right. The split between acoustic model and language model. The acoustic model is the part of the speech engine that maps acoustics, so that's a waveform, and a pronunciation model. So that's the waveform. I've made a little scribble here to designate the waveform. And this is to stand for voice in its the phonetic alphabet. The acoustic model is that part that is concerned with matching the phonetics to the audio. And in mathematical terms, this is described what's called a likelihood, and it's a probability, really. It says it's a probability that the audio is, as we observe, assuming that the phonemes are from a given word sequence. So it's probably the other way around from what you'd expect, right? It's really this sort of probability. It's not the other way around that we use it. We use it this way. And that's why it's called the likelihood. It's the likelihood of the word sequences, really. We do observe the audio, and we're trying to infer the word sequence at the point where we do recognition. The language model, instead, is the part of the speech engine that is used very heavily in what's called large vocabulary speech recognition. So that is the sort of speech recognition you're probably used to if you do dictation or if you use your mobile phone, because you'll be using natural language. You'll be using a very wide lexicon. Maybe you'll be using, words from a lexicon, typically of several tens of thousands of words, or maybe hundreds of thousands of words if you include proper names and things like this. So the language model is an important part to do prediction properly. This example here says the cat sits on the, and then the prediction model will assign a probability to the subsequent word, to every possible subsequent word, and it will assign a higher probability to those words which are more likely given the words that it's already seen. So that's the split. It's a very traditional split in speech recognition, and it's one that's been used probably since the 90s, since the time large vocabulary speech recognition as an engineering problem has ever been considered, actually. Right. When we put the bits together at runtime, we have this incoming audio here. We have a step called feature extraction that is signal processing, really. It's looking at the audio and it's extracting meaningful parameters from small windows of signal here. And this is what I've noted O then. It's the features, the things that we've extracted from the audio. And there's this big search box here, which is using as underlying data the acoustic model, the language model, and then the correspondence between phonemes and words. So it's called a lexicon or pronunciation model. And in mixing all these bits, it's going through all the possible hypotheses for sequences of words, and it's doing this search. It's considering all the candidates. It's a massive search. Obviously, the very sort of refined engineering optimization techniques here. And it's trying to find the one sequence that is best. And it's actually, as I described before, outputting several possible candidates, and maybe the application itself is in a position to choose the best candidate sequence based on some knowledge that the application has, but that the speech engine doesn't have. Right? So that's the reason why here you'll actually be seeing things like candidate word sequences, and then a score like I don't know, 57% maybe, right? And then you'd be having the next one, and that's only got a 43% match. Okay, if you want these things to add up, then that's another business. If you have several more here, but you can normalize this if you want. Otherwise, they're just scores. So that's when you put the bits together. Going back to the feature extraction step, because that's one that enables you to understand how the acoustic model then works. And I'll be trying to get into a bit of the mechanics of the speech engine here. Don't be afraid by the details, but these are important to understand to sort of pinpoint where exactly deep learning has been making this huge difference in performance. So this is it's called a spectrogram. It's a very colorful representation for speech. This is the axis for time. And this is a decomposition of the speech signal in frequency. And what I've drawn here are the slices. Usually they're like 10 millisecond slices that we make of the speech signal. And we take each of the slices, they're called windows, and we compute these features on each of these windows, right? And then we feed this into a model, the Hidden Markov Model, that consumes one of these slices at a time. And the Hidden Markov Model is probably a thing that you can visualize pretty easily if you've done computer science before, because one way of looking at it is very much like a finite state automaton. So this is a representation for a Hidden Markov Model that encodes a speech recognizer able to recognize two words, of which I've written down the phonemes here, namely yes here and no here. So the finite state machine has an entry node and it has an exit node, and you will actually move from entry node to next node to middle node to end node, and then to the exit node to signal that you're done. Every time you move from one node to the next, or maybe from one node to itself over this re-enter loop here, you will eat one of the slices I've shown on the slide before. So this is how the finite state aspect of things works. And you will, in the decoding step, you will walk through all possible steps, all the possible paths through this finite state machine, and you'll be calculating scores for each of the paths, right? So that means to calculate the score, you'll have a model, another probabilistic model here, that is called the emission model for a given phoneme. So here I've taken the phoneme E, that's in the middle of this yes word. And it's a model that eats a window of speech features. So I've represented this by just taking a slice of the spectrogram before, eats this, and outputs a probability that the audio was produced, assuming that we're in the phoneme step or in the phoneme stage A, if you like. Okay? So as I eat, from the slide before, as I eat each of my little windows of speech here, I'll be making my way through the HMM that you can imagine could be way bigger if it's got many words, and maybe it's got branches because words might have different pronunciations, or parts of words might have different pronunciations. And then you've also got to consider all the re-entering loops. So it's a huge number of combinations you're actually looking at. And when you arrive at the exit node, then you've got a candidate path that actually matches the length of the expected words. And among all these, you will be outputting the probability for each of these, and then you'll be looking at the one with the best match. This is almost the entire truth. The only variation, the only complication that is in actuality, so that is in real speech recognizers, is that HMM states for each phoneme, they're not actually one one node. They're actually made of 3 nodes. And that is because you've got what's called a co-articulation effect, which is the fact that each phoneme is affected by the neighboring phonemes. So the beginning of A will be affected by the fact that there's a Y before, and the end of yes, it will be affected of the A phoneme. It will be affected by the fact that we are then pronouncing a S as the last phoneme. So that's why people have been splitting up these things in 3 different states, each of them with their own parameters as to how likely it is that you re-enter, how likely it is that you move on, and then the parameters that are actually in this emission model, which then is for not a phoneme, but for a subphonetic state. So maybe I've chosen this state here, which is the first state in phoneme A, preceded by Y, and followed by S, right? But apart from this, this is really what a speech engine used to be like, well, still is in many industrial cases, still is in the industry. That's how it works. So the big change that's happened is in this emission model. This emission model used to be a Gaussian mixture model. So a Gaussian mixture model is nothing else than a superposition of Gaussians. So if you draw this in, say, in 2D, a Gaussian probability says like, we've got a bump here, that's a Gaussian, say, and a Gaussian mixture model is an addition of several Gaussian bumps. So if I take another bump here, okay, and the sum of both is probably something like this thing here. I should probably change color, but you can see what I'm hinting at. Okay, so this thing with a double bump here, that's the sum of the 2 Gaussians. Hello, back we are. Okay, sorry guys. I'm not going to name the operating system that is playing with my nerves here. Let's get the slides back on. Oh, presentation software. This is PowerPoint. The waveform, I didn't say anything. The waveform is not Gaussian. What's Gaussian in the Gaussian mixture model is the form of the model. Remember that it's not modeling the actual audio. It's modeling the features extracted from the audio. We can come back to this later on. So the thing is then, big change is this Gaussian mixture model inside the hidden Markov model then, used to be used until I think, well, I'd say 2012 or so as the industrial standard, as the state of the art. And then everything changed. And from then on, people have been using deep neural networks. And so here's a slide that shows what the state of the art is. So I don't have, any special insider's knowledge, but I guess that what's used in industry in big recognition software or in big sort of machine learning companies looks very much like this. So they have an architecture that uses about 5,000 or 10,000 of these subphonetic HMM states. These things are actually called C-nodes. And a typical DNN architecture will have these 5 hidden layers, maybe 2,000 nodes each in breadth. We'll have as many output nodes as C-nodes because we'll have a classifier model, which will take audio features as the input, and it will classify these into a C-node. So it will produce as the output which subphonetic HMM state this audio could be coming from. Where the standard, again, is to use rectified linear units and the cost function cross entropy, but this is a technicality. You don't need to be worried about this usually. But still, one interesting bit is that still in state of the art, in many, many cases, you use a GMM HMM, so the old style speech engine, as a preliminary step when you do training in order to produce the state inventory that you're dealing with. So the states are the C-nodes, and also in order to align the training audio you have with each window of audio too. Okay, so this step, people have been trying to do this with just the DNN-based speech recognizer, but it turns out that it's still working a bit better in different cases. It's still working a bit better, still using the old-style speech recognizers for a variety of reasons. So this is what industrial state-of-the-art is like now. The setup then looks like this. You've got the input here from let me show the laser pointer. The input here from the feature extraction step, and then different steps of pre-processing to get you to the point where you have the input features. So these things that get into the input layer of the DNN, right? And then you feed this through the hidden layer, and you've got a softmax output layer, which will produce as their output one of the C-nodes you're looking at. Okay, this, well, a big, say, publication, an important publication that showed that, or that really defined this as the new state of the art, was this paper, the Deep Neural Networks for Acoustic Modeling and Speech Recognition. Was published in 2012 in the Signal Processing, the IEEE Signal Processing magazine. And what's interesting about this article is that very uncommonly, this was co-authored by 4 research groups. And that was the University of Montreal, Microsoft Research, IBM, and Google. And so these 4 research groups had were seeing the same improvements in their experiments. Namely, they were going from these traditional models, the GMM-based models, and they were seeing error rates of 23%. And then they were using deep learning-based models, and they were dropping their error rates by 1/3 or so, just by changing the acoustic model. And that is something that is totally unseen. Up to then, increases in performance had always been by 1% each time, or by a couple of percent relative here. Okay, never before had people seen just a single jump in performance so high at once. The other big innovation that I was hinting to is the one in the language model. So typically before 2010, you'd be using a prediction function that says how likely the current word is, given that we've got a history of previous words. So this bit here would be the cat sits on the, and this would maybe be mat, or it would be chair, or it would be before. Obviously, before is not likely to appear in the sentence, the cat sits on the before. That's unlikely, right? So the probability here will be low for before and will be higher for things like chair or mat. And what was happening before 2010, 2012 then is that people were using a model called n-grams, which are a very simple thing. They really are counts of how often have we seen this sequence of words in the data, in training data, so in text data. How often have we seen these this sequence of words? And then based on this, we do counts, and that's the basis for which to predict the next word. Okay, so the n-grams, and then back-off models, obviously, when you haven't seen this sequence of words, in some way you try and guess, maybe on a shorter sequence of words, what could be the probability of the upcoming word. And the new model that's being used these days is recurrent neural networks, language models. So they're pretty simple architectures. You're representing your input word by a one-hot vector. So these are all zeros except this black dot here, which figures a 1, and all zeros again. So this is a big vector. Usually it's as large as your vocabulary. So you can think of it as a vector that's 100,000 positions long with only one 1 here, and the rest is zeros. You're turning this into a vector of much smaller dimension. And then you're producing through a softmax layer in a neural network, you're producing a probability for the next word. So this is, again, a very long vector that's about 100,000 long. And what makes it recurrent is that you'll be adding the same architecture for the word before. That's the thing I've noted, WT minus 2, and then for the word still before, WT minus 3, and so on and so forth. So you've got this recurrent neural network language model. You've got a couple of technical issues appearing, these vanishing and exploding gradients things. So you've got LSTM as maybe a better version of the RNNs. And this is something that brings you another 10 to 20% relative word error rate improvement. So using these two tricks, using deep neural networks in the acoustic model and using RNN language models, you are achieving maybe a 50% increase of performance. And this is along with the availability of a ton of audio data. This is really what has been decisive in making speech recognition mainstream on smartphones, really. Okay, I'll be saying a couple of words. So active research areas. Very interesting thing is people are starting to try to do feature extraction, so the very first step, in a way that is totally guided or that is totally learned from data. So far we had things that were totally engineered. That's what I mean here by carefully engineered. We've got this technologies called MFCC or perceptual linear prediction or gamma tone filters. MFCC is for male frequency capsular coefficient, so barbaric engineering signal speech processing methods, and then a diversity of methods to try and make them take away covariance or take away interdependence between windows of speech. These are things that are still state-of-the-art to be used in DNNs, although in a much simpler fashion. There's no real unanimity on how to best do pre-processing like feature extraction when using DNN acoustic models. But what's currently under investigation in research groups is, what if we feed our acoustic model with the raw signal? We don't do any pre-processing at all. And what happens is that it seems that our neural networks will learn to do exactly the kind of filtering that our filters were doing before, the ones that we were engineering as carefully as I described. So these are two plots from two different methods, the references of which are here, which seem to each of the horizontal lines represent the frequency at which a given maybe neural unit is extracting, and they're really nicely ordered. If you reorder them, then you can see that they go from the low frequencies to the high frequencies, and they're really looking at the frequency spectrum that is actually interesting in speech, so things that are going on between 0 and 4 kilohertz, right? So the majority in number of the filters here, right? These guys here, so maybe 3/4 of the filters are actually going at the bits that are interesting to do speech recognition, and they've learned this by themselves. And then the end-to-end systems are the ones which do away with this HMM thing altogether, and instead they have a recurrent neural network architecture with an adequate structure. And so they do away with this HMM thing altogether, which simplifies the pipeline a great deal, fixes a lot of the issues we've been seeing with HMM, typically duration modeling. So how long are you staying in in one of these states, right? Duration modeling is obviously given by how likely it is to re-enter the state. How often am I looping here? And duration modeling is a thing that's not obvious in HMMs. And so these end-to-end systems sort of work in lab environments these days. But the state of the art in industry is still what I've been describing before, because we've got highly engineered, super tuned real-time decoders, and the bar is very high for these systems to actually beat the existing industrial state of the art. Okay, so here's a picture of interspeech in September earlier this year. There are two poster sessions going on here. One is novel architectures for large vocabulary speech recognition, and the other session is speech and music analysis. I'll tell you which is the neural net focused crowd. You've probably guessed that it's a denser one. So there's clearly a hype going on here, right? But you should be careful and not necessarily trust the hype, because it's not always a good idea. There are invariants in the speech community that people are seeing that don't have to do with the underlying machine learning model that you're looking at, and that still must be considered, still must be taken into account. So robustness and adaptation, what's happening if you've been training with training data that doesn't fit your test conditions, as in the speaker, or the noise conditions, or the channel, or the topic maybe. And then issues that have to do with speech as a much broader thing than just a sequence of words. So prosody, the melody of speech, what's going on in dialogue at all. And then the very hairy issues of what's happening with dialogue understanding, trying to make sense of speech, not only being able to do dictation, i.e. transcribing a sequence of words, but actually understanding what's going on. And then, all the engineering, data collection, footprint, latency issues. So these are the real issues that people are still looking at. And I would venture to say that the fact that you're using deep learning, so neural net-based models, as opposed to the other things that we were using before, HMMs or Gaussian mixture models or whatnot, this is not as relevant as the fundamentals in speech recognition. Thanks. We've still got a few minutes for questions, so I'm reading your chats here, and please shoot ahead, and I'll be taking your questions as you type them in. So I've got a question here. Has anyone looked at vocal phase information in the audio signature? So I assume your question means in the speech signal, and tell me if I'm misinterpreting your question. Signal in temporal signal in general, there's a phase information. There's what's being looked at mainly is amplitude in different frequencies in the spectrum, and in speech research there has been very little attention paid to the phase information. That's absolutely true, and it's actually an issue for microphone makers. I was speaking to a microphone maker a couple of months ago who was totally concerned about this, and he was surprised that no one had been looking at phase in speech recognition. So there is a bit of research on this. It's probably gaining traction because people think that the phase is a valuable piece of the signal to be looking at as well. And in fact, there's been an entire workshop session at Interspeech in September dedicated to this. It's probably quite easy to find on the web if you type Interspeech and phase workshop. I can find you the reference. If you can't find it, drop me an email. Is there a good, widely available package of algorithms to easily experiment with up-to-date algorithms? So you're saying in speech recognition, is there a nice, maybe software library that you can do speech recognition with, do experiments, vary the type of model you're looking at, and so on and so forth? Yes, there is. I would pick just one, Caldi. Let's type it in. It's KDI. This is a library, a speech recognition library that's called. It's pretty new. It's pretty good, and it's got a lot of the new stuff. So it's got deep neural nets, acoustic models, and stuff like that. So it's a pretty good place to start. It's a steep learning curve if you're starting from no knowledge of speech recognition at all. What technique would you recommend for building audible language back from the data? So text-to-speech technology. Right. So text-to-speech is a sort of sister technology to speech-to-text, clearly. There are people trying to do deep neural network-based speech synthesis, but mainstream methods are still based on concatenation of units, they're called. So concatenative unit speech synthesis. That's an entire set of different technologies. No, actually, I'm saying nonsense. I mean, it's probably been a couple of years now that people do parametric speech synthesis. This probably redefined the state of the art. Concatenative techniques were probably more like 5 to 7 years ago. I'm less of a specialist in speech synthesis and speech recognition, so maybe my knowledge was a bit dated. But no, parametric speech synthesis is the way to go nowadays. And well, you know, state of the art here, as in speech recognition. Deep learning, there are a couple of papers out, like people have been trying to do deep learning for speech synthesis, but that's not mainstream. Catching up with GPUs too, of course. Everyone is trying to make use of the Caldi. Yeah, that's Alison writing. Hi, Alison. Trying to make use of the GPU computing power on the smartphones if they're available. I don't know if speech recognition libraries running on smartphone these days make use of those architectures that have got GPUs. I'm not in the know here. I'd be curious to know. Text-to-speech open libraries, yes, there are a couple. I can't name them off the top of my head, but you can surely find them. Voice disorder classification. So deep learning applications. So I don't know if deep learning, I mean, you know, again, deep learning is just one of the machine learning techniques of others. Among others, so using a classifier based on a feed-forward neural network is probably, you know, as good as many instances as using a classifier based on a different set of models. Voice disorders are certainly an important field of study, and again, at Interspeech every year there's a lot of a large proportion of the papers and of the workshops dealing with things like detecting in speech, detecting signs of autism, detecting signs of drunkenness, signs of substance abuse, first signs of Parkinson's disease, and so on and so forth. There's a great deal of study here because the speech signal, as it's one of the most important biosignals, is affected by a lot of the cognitive disorders that are going on in our brains, and so it's a signal in which you can out of which you can read a lot of what's going on here. I don't know intelligent voice, but I'll be checking that out. Still waiting for more of your questions if you have any. Yeah. So I guess calling up the Interspeech website here. You probably want to go through the program, or the, what is it? Program, detailed technical program, and that will give you an example of what's going on in the speech community. Okay, new questions. Bandwidth bins used in the FFT voice analysis. So these are based on the MEL scale. You can probably Google and Wikipedia this. The MEL scale is a sort of perceptually based scale that tells you what the impact of each frequency band is in the audible spectrum, and it's used to indeed make these bins in the MEL frequency capsule coefficients approach, and also in the filter bank transform methods. So we are using bins that are sort of irregularly spaced in the band from 0 to usually 8 kilohertz or so of a signal. Books on the subject. There's a book that's come out by Li Deng that is very up to date. I'll try and conjure this up to find this for you. Deep learning, no, that's not the one. Deep learning methods and application. That's just on well, deep learning. Pretty, yeah. It's the automatic speech recognition book, right? I'm gonna paste the Amazon link here. That's the book I mean. So this is a pretty technical book. It's pretty useful too. So if you've got spare time, then that's probably a good place to start. Blogs. Not sure. Don't have any favorite blogs in speech recognition, but you can probably find some. Blogs you'll probably find either of software makers trying to advertise how good their speech recognition software is, or of researchers. And if you're interested in industry applications, obviously, then you need to bridge the gap between these two because they're not speaking about exactly the same issues. Is the processing of the speech recognition in mobile processed on the device? That's a good question. So different people or different companies use different techniques, I suppose. Mainly, the answer is no. Mainly, speech recognition, so large vocabulary speech recognition, is happening on the cloud. And the speech is compressed, sent over to the cloud, and the result is sent back. There are ways, and indeed, like on Android, if you're offline, your speech recognition, provided you downloaded the correct packages, it will happen offline. it will be of lower quality, so the results will be less good, but it will still, work to a certain extent, because the memory footprint of the models can obviously be way less big than what you can run on servers. And currently, the performance gap is still pretty big. So it's still running on the cloud, so on servers. Okay. I guess I'm done with my time, so I'll answer the last question that's come up. And then, if you find my email address, then you can drop me an email. Otherwise, I'll say bye-bye. Access to the slides, I'm going to check this with the organizers. You have access to the replays of the videos anyway, so that should be easy. Speech recognition API from Nuance to be the best for app development. Nuance is one of the providers for speech like cloud-based speech recognition. There are many others. There's Google Voice, IBM, HP, Speechmatics, very many. So Nuance is one of them. They're all pretty good, really. So I wouldn't necessarily say that one is totally better than another. They're all very, very good. So probably your choice will be based not only on sort of raw performance on a test corpus or sort of these kinds of numbers, but probably more on things like availability of languages, availability of features. Can you define your own custom vocabulary or pronunciation? Can you define your own language model, so sort of inflect recognition towards words that your users will be saying, and things like this. This is probably much more important than the actual word error rate that you're getting out of the engine. Thank you.